Good morning everyone. So what we're going to do today is just a continuation of what we've been doing in terms of Kirchhoff's law, resistances in series and parallel, and Ohm's law. You're going to use the PDF National 4-5 Applied Electronics, so this booklet, right? So this is the notes for all of the applied electronic stuff. You could read through it, see if you're having problems with stuff. As well as the data book being a resource for you, you can use the notes as well. What we're going to do is we're going to start at the notes on page 31. Just going to kind of talk you through what I want you to do. So that's, I'll put 31 in there thinking that was this is a worked example. So this is a worked example of a series circuit with two resistive elements in it. Shows you how to work out, there's what the question is, work out the total resistance, work out the circuit current, then work out the potential difference across both resistors. Potential difference is just a fancy way of saying voltage, so let's work out the voltage across R1 and the voltage across R2. So this is just an extension of the exercises that we've already been doing, and this is a worked example on page 31, so it shows you how to do it. That's how you do part A, part B and part C. And it talks you through. So there's notes before that, there's some kind of practical exercises that are done using, it says croc clips in there, obviously we use Yenka now. So there's some practical exercises in there on Ohm's law and stuff, and a wee exploration of circuits. So if you've downloaded Yenka for use at home, you can do those bits as well. Right, there's a worked example in series, and then on page 32 there's a set of questions to do, and they're only series circuits. And then there's a little exploration of what parallel is, what parallel means, and again, practical tasks. If you've got Yenka at home, you can do the practical tasks in Yenka. And then there's a worked example on parallel calculations. So there's how to work out the total parallel resistance. Their method, they keep it as 1 over RT all the way through, and they add those two fractions in the classical sense, the way you would have learned in maths, where you find a common denominator just by multiplying the two denominators, 270 times 100, which means that this guy has been multiplied by 270 and this guy has been multiplied by 100. So if you've got a common denominator in the bottom, you can just add the numerators. So that's why it becomes 270 plus 100 on the numerator line and 270 times 100 on the denominator line. And that's 1 over RT. So then you flip the whole thing upside down to give RT over 1 and flip that fraction upside down. So it's mathematically it's the same thing, it's just a different kind of process that they've went through to do it. Okay. So they work out total resistance and so on. I think this is another worked example, working out total resistance when there's 3 of them, and then a worked example where you're going to have to work out the circuit current and the individual currents. So I've already shown you that, but this is just another set of examples. And then on page 39 there's a bunch of questions on parallel circuits. Remember, in these circuits where it's only parallel, given a 9 volt supply, that means there's 9 volts across that resistor and 9 volts across that resistor. In this one there's a 110 volt supply, that means there's 110 volts across that resistor and 110 volts across that resistor. And then the same for that one at 240. In these ones that don't give you the circuit, I would suggest you draw the circuit. It'll help you understand it. And then it moves on to combined series and parallel. You've got a wee series bit and a wee parallel bit. So if you're working out the total resistance, you work out the parallel bit first, and in that case you would work out the parallel bit first and then work out the series after that. Remember and draw your equivalent circuits. There's a worked example on a combined circuit, and then on page 44 there's a bunch of questions. Okay, so what I'm going to do is I'm going to set this, and I want you to stop there. I don't want you to go into power yet, I just want you to do that stuff, because that's all Ohm's law, Kirchhoff's law and resistance, and that's all I want you to focus on. Right, now I'm going to give you because it's a double period today, so I'll give you a double period today and then another period after that to do this, so you've got a fair bit of time to get this work done. I'm going to ask you to put it into a OneNote page. So basically, normally people have been doing work, they've been uploading pictures of their work. And you were still doing it in an assignment. I'm going to show you what happens with the higher, right? Because this is what I do with the higher, guys, and it's really handy for me to mark it properly. So in the assignments at higher, what I've been doing is, come on. Setting the assignment. So look at student view. So they've got the notes that back it up. They've got the video of me setting the task, and then there's a OneNote page, and that's where you have to put your work. So you click that, it opens up your OneNote Jotter page, and then just insert your pictures into your OneNote page. Right, just insert a picture in there. And then that way, when I'm marking it, I can actually annotate it. I can give you notes and tell you, instead of typing that wee box and then you need to match the text in the wee box to the stuff that you've done, because there's going to be a fair bit of work in this. Okay, so take your time, read the notes, make sure you've done the previous exercises beforehand, and if you have any questions, ask me. Don't half-heartedly attempt this, because if you, this is important, this is part of the course, this is an every year's exam. If you can't do this, then you're not going to, you're going to drop marks in the exam when you get in next year. We can't afford to recover all this. We don't have the time to recover all this. You need to take the time and do it slowly and carefully right now. Okay? Right, all the best.